Module 2, Alternating Currents, Optical Instruments, Quantum Physics, and Semiconductors. Lecture 1, AC Circuit Theory. An alternating current, AC, is an electric current that periodically reverses direction, in contrast to direct current, DC, which flows only in one direction. The standard form of AC is a sine wave described as I(t) equals I sin omega t, where I(t) is the instantaneous current, I is the peak current, omega is the angular frequency. AC circuits contain resistors, R, inductors, L, and capacitors, C. The opposition to current flow is called impedance, Z. For a resistor, voltage and current are in phase. For an inductor, current lags voltage by 90 degrees. For a capacitor, current leads voltage by 90 degrees. Impedance combines resistance and reactance. Z equals square root a superscript 2 plus x underscore L, x underscore C, superscript 2. Where x underscore L equals omega L, inductive reactance. X underscore C equals 1/ omega C, capacitive reactance. The power in an AC circuit is given by P equals V cos phi, where phi is the phase angle between voltage and current. Cos phi is known as the power factor. Lecture 2, Theories of Magnetism. Magnetism originates from the motion of electric charges, especially electrons. There are several types. Diamagnetism, materials are repelled by magnetic fields, e.g., bismuth. Paramagnetism, materials are weakly attracted to magnetic fields, e.g., aluminum. Ferromagnetism, materials exhibit strong attraction and retain magnetism, e.g., iron. Domains are regions where atomic magnetic moments are aligned. In ferromagnets, these domains reinforce each other. Curie temperature is the temperature above which ferromagnetic materials become paramagnetic. Lecture 3, Optical Instruments. Optical instruments are devices that help us see and analyze light and images. Microscope uses 2 or more lenses to magnify small objects. Telescope, used to view distant objects. Includes refracting and reflecting types. Spectrometer analyzes light spectrum to determine composition. Camera captures and records images using a lens system. Human eye, natural optical instrument. The retina acts like a screen where images form. The lens formula applies to many optical instruments. 1/f equals 1/v, 1/u. Where f is the focal length, v is the image distance, u is the object distance. Lecture 4, Introduction to Quantum Theory. Quantum theory revolutionized physics by introducing the idea that energy is quantized. Max Planck proposed that energy is emitted in discrete units called quanta. E equals h nu, where E is energy, h is Planck's constant, nu is frequency. This theory explains phenomena that classical physics could not, such as blackbody radiation and the photoelectric effect. Lecture 5, The Photoelectric Effect. In the photoelectric effect, light striking a metal surface can eject electrons. Einstein explained it using quantum theory. E equals h nu equals phi plus k, where phi is the work function, minimum energy to eject an electron. K is the kinetic energy of the ejected electron. Important observations. No electrons are emitted below a certain threshold frequency. The number of electrons increases with light intensity. The kinetic energy depends on the light's frequency, not its intensity. The photoelectric effect provided key evidence for the particle nature of light. Lecture 6, Bohr's atomic model. Niels Bohr proposed a model for the hydrogen atom that explained atomic spectra. Key points. Electrons orbit the nucleus in quantized energy levels. Electrons can transition between levels by absorbing or emitting photons. Angular momentum is quantized. L equals N, H/2 pi. Energy levels. E_n equals minus 13.6 eV/n superscript 2. Where N is the principal quantum number. Bohr's model accurately predicted the line spectra of hydrogen. Lecture 7, Energy levels and line spectra. Atoms emit or absorb light when electrons jump between energy levels. The difference in energy determines the frequency of emitted light. Delta E equals h nu. Each element has a unique line spectrum, which acts like a fingerprint. These lines fall into series. Lyman series, UV. Bolmer series, visible. Paschen series, infrared. Spectra analysis allows us to determine the composition of stars and distant galaxies. Lecture 8, Matter waves and de Broglie hypothesis. Louis de Broglie proposed that matter, like electrons, also exhibits wave properties. Lambda equals h/p. Where lambda is the wavelength, h is Planck's constant, p is momentum. This idea led to wave-particle duality, the concept that particles behave both as particles and waves. Electron diffraction experiments confirmed de Broglie's hypothesis. Lecture 9, Band spectra and energy bands. In molecules and solids, we observe band spectra due to transitions between closely spaced energy levels. In solids, especially crystals, atomic orbitals overlap, forming energy bands. Valence band, highest energy band filled with electrons. Conduction band, higher energy band where electrons are free to move. Band gap, energy difference between conduction and valence bands. The size of the band gap determines the electrical conductivity of a material. Lecture 10, Introduction to Semiconductors. Semiconductors are materials whose conductivity lies between conductors and insulators. Examples, silicon Si and germanium G. Types. Intrinsic semiconductors, pure form, conductivity due to thermally excited electrons. Extrinsic semiconductors, doped with impurities to enhance conductivity. N-type, extra electrons. P-type, extra holes, positive carriers. Semiconductors are the foundation of diodes, transistors, integrated circuits, solar cells. Lecture 11, Summary of Module 2. In Module 2, we explored the following areas: alternating current theory and power calculations, various forms of magnetism and their applications, optical instruments like microscopes, telescopes, and cameras, the foundation of quantum physics and its revolutionary concept, the photoelectric effect as evidence for quantization, Bohr's model and the origin of atomic spectra, wave-particle duality and the matter-wave concept, the formation of energy bands and band spectra in solids, semiconductors and their role in modern electronics. These concepts help us understand both the microscopic behavior of particles and the technological applications that power modern devices. Course conclusion, General Physics 2. In this course, we have deepened our understanding of electric and magnetic phenomena, learned the principles behind electronic components and systems, explored quantum mechanics and its impact on our understanding of matter and energy, studied atomic and solid-state physics to explain everyday technologies. You now have a strong foundation to pursue advanced topics in physics, engineering, or any scientific field that depends on physical principles. Thank you for joining this lecture series on General Physics 2.